Hello everyone, welcome back to my channel. Today we're going to work through this problem of fluid mechanics and we're going to read through the problem first. The gate shown in the figure below is in static equilibrium about the hinge point O. The gate has a width W into the page. What is the specific gravity of the gate material? Hint, the center of gravity of a quarter section of a circle of radius r is 4r over 3 pi. So here's the definition of specific gravity. It is the density of the material over the density of water at 4 degrees Celsius. And the density of water at 4 degrees Celsius is 1,000 kilogram per meters cubed. So basically, this problem is basically we have a gate, it has some weight, and then we have hydrostatic pressures in the x and y direction. But one hydrostatic pressure that has two components in the x and y direction pushing against this gate to swing it outwards. But this gate has a certain weight, and this weight has a moment counteracting the moments produced by these x and y pressure forces. And so first, let's draw a free body diagram on our gate. So the gate has a weight acting on it. As a weight acting at the center of gravity, which we can call, actually, let's draw the picture bigger so that we have more to see. That should be big enough. Yeah, so the weight acts at the center of gravity and is located at a distance, let's call it xcg, center of gravity. And we also have a pressure force in the x direction and a vertical pressure force. So horizontal pressure force, which we will call FPH, and also a vertical pressure force that acts a certain distance from the hinge, and the hinge is at O. So the vertical pressure force acts at a distance, let's call it um, uh, XCP for center of pressure in the x direction, and the vertical component of the pressure force acts at a distance, let's call it X. Oh wait, sorry, Y, YCP. And so we have to find YCP and XCP. But first, before we do all that, we have to come up with the moment balance equation. So the sum of the moments about the hinge must be equal to 0 since nothing is moving, no water is escaping. And it's equal to uh well, the horizontal component of the pressure force is going to produce a clockwise moment since it's going to rotate this structure clockwise. So it'll be a negative moment. So we have negative horizontal pressure force times YCP. Uh, oop. And and a also a clockwise moment from the vertical pressure force, which is clockwise as well. Um, so minus FPV times XCP. Okay, and then we have a clockwise moment from the weight of the gate. So plus W, and this acts at the center of gravity, so XCG. So we have multiple unknowns over here that we have to find. And among them are YCP, XCP, and XCG. Well, xcg we know already to be 4r over 3 pi. So we can note that xcg equals 4r over 3 pi. Um, let's try to find everything that we can find already. So what is the weight of the gate? Well, as we know, the weight can be expressed in terms of the specific gravity because the specific gravity is the density of the gate over the density of water. So the density of the material is going to be the specific gravity of the gate multiplied by the density of water or rho H2O. And then density, this represents the density of the material. And I'll write it explicitly as the rho G, which is the density of the gate. And density times gravity, or first, let's do density times the volume of the gate. So what is the volume of the gate? Well, we can find the volume of a cylinder first and then divide it in four. Since the gate has a structure that is three-dimensionally that looks like this. So this is about 1/4 the volume of a cylinder, actually. So if we find the volume of a cylinder and then we divide it by 4, we should get the volume of the gate. So the cylinder has height of W and then the radius is R, of course. So volume of cylinder is pi R squared times W, and then you divide it by 4 to get the volume of the cylinder. So we have the density of the gate, and then if we multiply that by the volume, which is pi R squared W over 2, we should get mass. And then if we multiply, and let's just make it explicit, this is mg, the mass of the gate. And if we multiply mass by gravity, we will have weight. So the weight is equal to the specific gravity of the weight times the density of water times gravity times uh pi r square. So sorry, actually we divided by 4 since we actually divided the cylinder by 4 to get the volume of a quarter circle cylinder. Yes. So that is the final weight expression. Now we want to find um the pressure force, the horizontal component of the pressure force. And the horizontal component of the pressure force, what is the magnitude going to be? The horizontal component of the pressure force is going to be given in magnitude by the vertical projection of the area of the gate um, multiplied by, yes, the vertical projection of the area of the gate multiplied by the density of water multiplied by gravity and multiplied by the centroid of this vertical projection of the area. So first of all, how do we find the vertical projection of the area? This means if this face where we're looking at it is in the XY coordinate, XY directions, we try to look at the whole structure from this perspective, which is going to be what we call the mm, the XZ direction. So mm, let me see. How do we best describe this? Yeah. So let's say that the z-axis is pointing directly outwards at us now. So if we have the z direction be pointing to the left now, now the x-axis is pointing outwards. We'll have the y-axis here. So if we look at it from this perspective, then this is going to be the vertical projection of the area. So the vertical projection of this area over here, and it's actually going to look like a rectangle. We have R over here, we have W over here. So the vertical projection of the area um, is equal to RW. That's the vertical projection of the area. So this vertical projection of the area is going to have an associated centroid. And the centroid is located at a distance r over 2. So it's going to be r over 2. So, oops, sorry, this is not the vertical projection of the area. Yeah, the vertical projection of the area by itself is RW. So the horizontal projection of the force is going to have magnitude of, first of all, rho of H2O times G, and then times RW, and this pressure force has magnitude um, at the centroid of the vertical projection of the area, which is going to be at a distance of r over 2, as we said earlier. So simplifying, we have that the magnitude is equal to rho H2O times G times 1/2 times R squared times W. Now it's time for us to find the uh, vertical component of the pressure force. What is that one going to be? Well, don't forget that the vertical pressure force for a curved surface is equal to the weight of the liquid above it. Is equal to the weight of the liquid directly above it. That will be the vertical pressure force. And the weight of the liquid above it is going to be 1 over 4 rho of H2O times gravity times pi r squared times W. And another way of thinking about how to get the vertical pressure force is from buoyancy. Buoyancy states that the amount of displaced fluid, the weight of the displaced fluid is equal to the buoyancy force. And that is in turn going to be your vertical pressure force. Because buoyancy always points vertically upwards. Basically, the horizontal component of the hydrostatic force acting on a surface is equal in both magnitude and line of action to the hydrostatic force acting on the vertical projection of the curved surface, while the vertical component of the hydrostatic force acting on a curved surface is equal to the hydrostatic force acting on the horizontal projection of the curved surface plus the weight of the fluid block. So in this case, what is the weight of the fluid above this curved surface? Or in other words, what is the weight of the what is the weight of this fluid, of this volume of fluid? So now we have a similar problem as what we found for the weight of the gate, except now instead of specific gravity, we don't need specific gravity anymore. We only need the density of water since we want to find the weight of this volume of water. So we can simply use what we calculated here and just take this portion. So then that is going to be rho of H2O times pi r squared W over 4 times G. Um, yes. So that is going to be the vertical component of the pressure force. So now we have found horizontal component, vertical component, and the weight. And we also know XCG. Now what remains for us to find is YCP and XCP, the locations of the center of pressure. Center of pressure can be a confusing topic because you must not confuse it with the centroid. And uh, and I found a good explanation on using AI. I think they explained it perfectly, and I'm going to show you right now. So basically, ChatGPT summarizes it pretty well. There are two key concepts in hydrostatics. One is the hydrostatic force concerned with the magnitude. And on a plane surface submerged in a fluid, this is equal to the force is equals to rho, the fluid density, times g gravity, times y bar, which is the depth to the centroid of the surface, times a, this area of the surface. This is exactly what we used just now to find the vertical component of the pressure force, FPV, and the horizontal component of the pressure force, FPH. However, and we use the vertical projection of the area, and we also use the centroid of the vertical projection of the area. However, the center of pressure or the location of the resultant force is different. It's not located at the centroid of the surface. In fact, it's often located at a location lower than the centroid because of how pressure increases with depth. So, and the center of pressure is given by this equation. YCP is equal to Y bar plus IG over Y bar times A. So IG is the second moment of area around the centroid's horizontal axis, and YCP is the depth of the center of pressure from the fluid surface. I think they mean Y bar over here. So why you need both? The magnitude F tells us how much force is exerted by the fluid, and the center pressure tells you where that force acts, which is not at the center unless the pressure is uniform. That is a horizontal surface. This is crucial when you analyze moment equilibrium like gates, dams, and doors, and when you calculate torques caused by fluid pressure, and when you calculate moment, as we are doing right now. That's why we need to consider the center of pressure. And it's also useful in assessing the stability of submerged bodies. So in a quick summary, hydrostatic force is given by this equation, and center of pressure is given by that equation. Hydrostatic force is the total fluid force on the surface, while center of pressure is the location of the force below the free surface. There are a few shortcuts to calculating center of pressure that we'll be utilizing right now. So although we drew our diagram over here, it's often helpful to also draw one with a control volume, and that's exactly what we're going to be doing right now. So in a drawing with a control volume, we still have our quarter circular gates, and now we're going to have a control volume. We are going to call this one our control volume. And thus, there's going to be a pressure distribution acting on this control volume. And this pressure distribution is going to look something like this along the vertical face. And this makes sense because the pressure varies linearly with the depth. So at the top it's going to be zero since there's no pressure. But as you go down, it varies and increases linearly. That's why the magnitudes of the arrows are getting bigger. And this one is going to be from the horizontal pressure force. So this is the distribution of SPH. And what about the vertical pressure force? Well, the vertical pressure force is going to be uniformly distributed, just pointing upwards, since we are at the same depth at all points. As you see, the depth here is constant. That's why the pressure over here is going to be constant as well. Um, and this is the distribution for the vertical pressure force FPV. Now, where is the center of pressure for FPH? In other words, where is it acting? We can also see this on this formula sheet that x prime is representing the x component of the center of pressure, and y prime is representing the y component of the center of pressure. So we want to try to use this equation to find where exactly the center of pressures are located at. Basically, for a triangular distribution like this, we know that the location or the y CP is equal to r over 3. But let's see if we can prove that using our equation, because this equation is more versatile and is going to be applicable to all types of different cases. Um, let's first write down the equations here and define variables. So as you see right here, y bar is the depth to the centroid of the surface from the free surface. Ig is the second moment of area, or the area moment of inertia about the horizontal axis through the centroid. And A is the area of the surface. So this formula works for any arbitrary shape and any pressure distribution as long as the pressure still varies hydrostatically. That means it varies linearly with depth of pressure equals rho times g, gravity, times y, depth. So I guess over here we will use yc equals the distance from the free surface, which is located here, to the centroid of the projected area, which I'm assuming is the area they're talking about. So it's going to be r over 2. YC is going to be equal to r over 2, as we found previously from this projected area over here. And what about, what about IXC? IXC is the second moment of area, or the area moment of inertia about the horizontal axis through the centroid. So about the horizontal axis through the centroid. Yes, so we'll go to our table of values. As you see over here, we have a few area moment of inertias, and we want the second moment of area about the horizontal axis through the centroid. So, and conveniently, they even give you some values. As you see, IYC is equal to this, and IXC is equal to 1 over 12 BA to the power of 3. So we're going to use IXC over here. So as you saw just now, IXC is equal to 1 over 12 BA cubed. Now, what is our B? B is like the longer side. It's going to be the width. As you see over here, it's going to be the width. That's going to be B. And then A is going to be R. So B over 2 is going to be W over 2, and A over 2 is going to be R over 2. So, oops, I forgot to move something. Ah, yeah. So B is going to be, yes, B is going to be W, A is going to be R. So that's going to be 1 over 12 WR cubed. What about the area? What is it going to be? Well, the area is the area of the projected area. It's going to be R times W. So this means that Y prime or YCP, the center of pressure, is going to be equal to R over 2 plus 1 over 12 times BA cubed over RW times R over 2. This is going to be equal to R over 2. Oh, wait, sorry, I forgot to plug in the actual BA cubed. So WR cubed over RW times R over 2. This is going to be R over 2 plus, we're left with R squared, and the W's cancel out. 1 over 12 R squared over R over 2 is equal to R over 2 uh plus uh what? 1 over 6 or R over 6. So R over 2 plus R over 6 is going to be equal to 2 over 3 R's. Hold on, did I do something wrong? Let me check. I used ChatGPT to verify if I did it correctly or accurately, and it seems like I did. Um, but using this equation, keep in mind that it actually gives you the location from the free surface. So that's something you have to remember. So we'll add from free surface. But what about from the origin, which is the one we are actually concerned with? But from the origin, uh, it will be R minus 2 over 3R, which is equal to R over 3. And this is equal to our YCP value. Now it's time to find the X prime or the location of the center of pressure in the X direction. And this is equal to, let's see, this is equal to XC. Let me just verify that equation quickly. Yes, that's equal to XC plus IYC over AYC. So again, XC is the location of the centroid of the projection. And this time the projection we are actually concerned with is going to be the horizontal projection of the area. So the horizontal projection of the area is actually going to be identical to the vertical projection of the area since this is a quarter circle. So it's actually going to be uh also a rectangle of R by W. And it's going to look something like this, R, W. We want to find the location of the eccentroid, so XC. And that is going to be equal to, let me see, so it's going to be equal to, I believe, R over 2 as well, since this distance horizontally is R over 2. So XC equals R over 2. Or what is IYC? Well, we know that A, first of all, is going to be equal to RW as well. And yeah, okay, YC we already found from the other part. YC is equal to R over 2. So now we need IYC. So I think that for XCP, we cannot use the standard center of pressure equation. XCP is equal to X bar plus IYY over X bar times A, because that formula applies to flat surfaces under linearly varying pressure. But here, the vertical force is equivalent to the weight of a fluid volume, so it acts simply through the centroid of that volume. So here, XCP is equal to 4R over 3 pi, which is also the center of gravity of, of the quarter circle. So when to use this? When the vertical component of pressure on a curved surface is modeled as the weight of fluid above it. The point of application is at the centroid of the fluid volume above. For a quarter circle, centroid is 4R over 3 pi, comma, 4R over 3 pi. When not to use this is if you were computing pressure distribution on a flat vertical wall, you'd use XCP equals X bar plus IYY over X bar times A. But that's not applicable to curved surfaces like this one, unless in the case of our, I guess, vertical projection, it was applicable. So final answer is XCP equals 4R over 3 pi. Um, and I'll show you another way to get that actually from the YCP we found. So we can actually also find this from our YCP, since basically we know that the pressure force distribution on a quarter circular area is always perpendicular to the surface at each point. That's simply a known fact. And because of that, we know that the resultant pressure force must pass through the center of the semicircle. Basically that our horizontal component and vertical component must sum up to a resultant force that pass through the origin. So to find XCP, first note that the line of action for the resultant pressure force must pass through the origin of the gate, since the pressure force is everywhere perpendicular to the gate surface. So this means that so thus we can come up with a formula. So this one is YCP. We want to find XCP. We have theta over here. So this means that tan theta is going to be equal to the horizontal pressure force over the vertical pressure force. So the horizontal pressure force is going to represent uh, this one, this side over here, and the vertical one is going to represent this side over here. So tan of theta is equal to FPH over FPV. And this is equal to rho H2O times G times 1/2 R squared times W over 1 over 4 rho H2O times G times pi times R squared times W. And this simplifies to 2 over pi. So next, since we know the vertical location of the horizontal component of the resultant pressure force, we can determine the horizontal location of the vertical component of the resultant pressure force. Basically, y prime center of pressure is equal to m times x prime center of pressure plus b. So this means 2 over 3r is equal to tan pi over 2 minus theta xcp prime. So this means that 2 over 3r is equal to 1 over tan theta xcp prime. And this means that 2 over 3r times 2 over pi is equal to x prime cp is equal to xcp is equal to 4r over 3 pi. And this makes sense from the explanation we found in the AI because for the vertical one, we took the vertical pressure force to be equal to the weight of the water above it. And the weight of the water above it must act through the centroid. If that makes sense, because weight always acts through the centroid. So it must act through the centroid of this semicircle. And here we have our x prime and y prime directions. And okay, also known that not applicable here because this is a curved surface. The only reason why for the vertical surface it was applicable is because we used the vertical projection of the area. Because we're allowed to do that for vertical surfaces. So now all that remains is to substitute the known values and solve for the specific gravity from our moment equation way back here. So it is now finally time to plug in known values. So this is equal to FPH, which is rho H2O times G times 1/2. Okay, rho H2O times G times 1/2 R squared times W. And then YCP is we found to be R over 3. And then FPV we found to be rho H2O pi R squared W over 4. Don't forget the signs. Pi R squared W over 4 times G. And then XCP is, of course, 4R over 3 pi. And then W, we found the weight to be SGG, okay. Mm, pi R squared W over 4G. Okay, and then XCG is also 4R over 3 pi because center of gravity over here is they give us 4R over 3 pi over here. All right, so now it's time to combine and simplify because the hardest part is already over. Notice that this is all equal to 0, so we can divide out like common terms and move it over to the left side. So we see each of these terms have rho H2O, so we can go ahead and cancel them. They all have gravity. Let's go ahead and cancel it out. They all have R squared. Let's go ahead and remove that. They all have another R actually. So let's go ahead and just eliminate that. And they all have a okay, so the pi's over here to cancel out as they do over here. And we all have a weight. So actually so many things cancel out, which is really, really, really nice. And we are left with let's see, negative 1/2 times 1/3, which is negative 1/6. Negative 1/3 because the fours cancel out too. And then we're left with the fours cancel out, so plus 1/3 SGG. This is equal to 0. So then this means 1/3 SGG is equal to 1 over 6 plus 1/3, which is equal to 1/2. So SGG is equal to 1/2 divided by 1/3, which is 3 over 2. And this indeed matches our answer that we expected. Thank you guys so much for watching this video with me. I hope this video was helpful. It was a little more all over the place, but I hope it was cohesive for you guys in the end. Here's a quick scroll through everything that we went through in this problem. And don't hesitate to ask me any questions you might have in the comments below. I'll be posting these slides as well, as usual in the discussion section. See you guys next time.